Graphitization damage mechanisms is part of mechanical and metallurgical failure mechanisms. Description of graphitization. Based on API 571, graphitization is one of the general varieties of damage mechanisms in all industries, particularly is a part of mechanical and metallurgical failure. Graphitization is a damage mechanism that primarily affects materials exposed to extreme temperatures, particularly in metallurgical processes or high-temperature environments. This phenomenon is characterized by the transformation of carbon-based structures into a graphitic form. It is significant in materials science and engineering, particularly in the context of metals that contain carbon, such as cast iron and certain steels. There are some mechanisms of graphitization. Number 1 is thermal activation. Graphitization typically occurs at elevated temperatures, usually above 1000 degrees Fahrenheit. At these temperatures, the carbon atoms in a material can become highly mobile, allowing them to rearrange themselves into a graphitic structure. Number 2 is carbon redistribution. During graphitization, carbon atoms can migrate within the matrix of the material. This redistribution can lead to the formation of graphite particles, which disrupts the original microstructure of the material. Number 3 is phase transformation. The transformation from a more amorphous or disordered carbon structure to a more ordered graphitic one changes the mechanical properties of the material. The presence of graphite can decrease hardness, increase brittleness, and alter tensile strength. Number 4 is microstructural changes. As graphitization progresses, it can lead to the coalescence of graphite particles, resulting in larger, more interconnected graphite phases. This process can further compromise the material's structural integrity, leading to localized weakening and eventual failure. Number 5 is influence of alloying elements. The presence of alloying elements, such as silicon, manganese, or chromium, can either inhibit or promote the graphitization process, affecting the mechanical properties of the material. For example, silicon tends to encourage graphitization in cast iron, leading to a more desirable microstructure in certain applications. Implications of graphitization damage. Number 1 is mechanical property changes. The formation of graphite can significantly alter the mechanical properties of the material, affecting its hardness, strength, and ductility. Number 2 is thermal conductivity. Graphitic structures typically have high thermal conductivity, which can affect heat dissipation in engineered components. Number 3 is fracture behavior. The presence of graphite can lead to changes in the fracture behavior of the material, making it more prone to brittle fracture under certain loading conditions. And number 4 is service lifespan. In high-temperature applications, graphitization can lead to premature failure of components, impacting their service life and reliability. Affected materials. Based on API 571, graphitization can happen to some grades of carbon steel and 0.5 Mo steels. Graphitization damage is a process primarily associated with materials that undergo changes in their microstructure due to exposure to high temperatures, particularly in the presence of carbon-containing environments. This process can lead to mechanical degradation and changes in physical properties. In general, the affected materials typically include: Number 1 is graphite and carbon-based materials. Graphitization directly affects materials that contain carbon, such as graphite electrodes, carbon composites, and various carbonaceous materials used in industrial applications. Number 2 is metallurgical alloys. Certain metal alloys, especially those containing significant amounts of carbon, can experience graphitization, especially in high-temperature environments. This is notable in cast iron, where the carbon may restructure into graphite. Number 3 is ceramic materials. Some silicon-based ceramics may also experience graphitization under specific conditions, especially those that contain carbon or are designed to operate in high-temperature environments. Number 4 is composite materials. Polymer matrix composites that have carbon fillers or coatings can undergo changes in their properties due to graphitization when exposed to high temperatures, altering their mechanical strength and thermal stability. Number 5 is concrete and building materials. in some cases, concrete and other building materials can be affected by graphitization processes, particularly in environments where high temperatures are coupled with carbon sources. The mechanism primarily occurs under conditions of heat treatment, thermal cycling, or exposure to reactive environments, leading to a restructuring of the material's carbon content into graphitic forms, which may result in changes in ductility, strength, and overall material integrity. Critical factors of graphitization. Graphitization is the process where carbon materials transition to a graphitic structure, can be influenced by various damage mechanisms, particularly in the context of materials science and engineering. There are several, 12, critical factors that can contribute to graphitization damage mechanisms. Number 1 is temperature. Elevated temperatures can accelerate graphitization processes and affect the stability of carbon structures. At high temperatures, carbon atoms may rearrange, which can lead to defects and weaken the material. Number 2 is pressure. The application of pressure can influence the density and structural integrity of carbon materials. In some cases, high pressure can promote graphitization, while in others, it can lead to unwanted structural transformations. Number 3 is chemical environment. The presence of certain chemicals, such as oxygen, hydrogen, or boron, can affect the stability of carbon structures and promote graphitization or oxidative damage. Number 4 is impurities and doping. The presence of impurities can disrupt the carbon lattice and facilitate structural defects during graphitization. Doping with other elements can alter the electrical and physical properties of the material, impacting its overall performance and longevity. Number 5 is microstructural features. The initial microstructure of the carbon material, including grain size, orientation, and phase distribution, can greatly influence the extent and uniformity of graphitization. Number 6 is mechanical stress. External mechanical stresses can introduce cracks and dislocations in carbon materials, which can act as sites for graphitization or may hinder the process, leading to localized damage. Number 7 is duration of exposure. The time a carbon material is subjected to elevated temperatures and other stressors can impact the extent of graphitization and subsequent damage mechanisms. Number 8 is thermal conductivity. Variations in thermal conductivity can lead to uneven temperature distributions within the material, which can result in localized overheating and damages during graphitization. Number 9 is cooling rate. The rate at which a material is cooled after being exposed to high temperatures can influence the final microstructure and may lead to the formation of defects or residual stresses. Number 10 is phase transition behavior. Understanding how carbon transitions from one structural phase to another, e.g., from amorphous to graphitic, is crucial in predicting potential damage mechanisms during processing. Number 11 is surface reactions. Graphitization can be influenced by surface reactions, including oxidation or contamination during processing, which can weaken the overall structure. Number 12 is electrical and thermal properties. Changes in properties like thermal expansion, electrical conductivity, and thermal shock resistance can affect material integrity during the graphitization process. Understanding these critical factors is essential for researchers and engineers working with carbon materials to optimize their processing conditions and improve material performance while minimizing damage. Graphitization affected units or equipment. Graphitization is a damage mechanism primarily affecting materials that contain carbon, especially in high-temperature environments. It is characterized by the transformation of carbon bonds in a material, leading to the formation of graphite. The following, 7, units or equipment may be affected by graphitization. Number 1 is high-temperature reactors. Equipment like nuclear reactors or chemical reactors that operate at elevated temperatures may experience graphitization in components exposed to high thermal and radiation conditions. Number 2 is heat exchangers. In certain processes, heat exchangers made of carbon-containing materials may undergo graphitization, affecting their efficiency and structural integrity. Number 3 is pipelines and pressure vessels. Carbon steel or alloyed materials used in high temperature and high pressure conditions, especially in petrochemical or hydrogen environments, can be susceptible to graphitization. Number 4 is boilers. Components of boilers operating at high temperatures can also experience graphitization, particularly if they are made of carbon-rich materials or exposed to conditions that promote such a transformation. Number 5 is turbine components. In turbines, especially gas turbines, parts that are exposed to extreme temperatures may be prone to graphitization, which can compromise their performance. Number 6 is reforming units. Equipment used in processes like catalytic reforming in refineries may be at risk due to high operational temperatures and the presence of carbon. Number 7 is coking units. Coking processes, which involve high temperatures, can lead to graphitization in the machinery and piping used in these processes. Understanding the potential for graphitization in these units is crucial for maintenance and failure prevention, as graphitization can lead to significant material degradation and operational failures. Regular monitoring and inspection of affected equipment are essential to mitigate the risks associated with this damage mechanism. Appearance or morphology of damage. Based on API 571. The first is, damage due to graphitization is not visible or readily apparent and can only be observed by metallographic examination, see Figure 4.1 and Figure 4.2. And the second is, advanced stages of damage related to loss in creep strength may include microfissuring/microvoid formation, subsurface cracking or surface-connected cracking. Graphitization is a damage mechanism that occurs in certain types of graphite or composite materials under high-temperature conditions. The appearance or morphology of graphitization damage can vary depending on the specific material and environmental conditions, but here are some common characteristics. The common characteristic of appearance or morphology of graphitization damage. Number 1 is graphitic flakes. Graphitization can lead to the formation of graphitic flakes or plates, which are flat, smooth, and layered structures. These flakes can be oriented randomly or in a preferred direction, depending on the material's crystal structure and processing history. Number 2 is graphite layers. Graphitization can cause the formation of parallel graphite layers, often with a well-defined crystal orientation. These layers can be separated by amorphous or defective regions, which can lead to a layered or flake-like morphology. Number 3 is lamellar texture. Graphitization can result in a lamellar texture, characterized by alternating layers of graphite in other phases or voids. This texture can be observed in both polished and etched samples. Number 4 is graphite nodules. In some cases, graphitization can lead to the formation of graphite nodules or aggregates, which can be several micrometers in size. These nodules can have a distinct shape or morphology, depending on the material's processing history and thermal exposure. Number 5 is graphite fibers. Graphitization can cause the formation of graphite fibers or whiskers, which are thin, elongated structures that can be several micrometers in length. These fibers can be oriented randomly or in a preferred direction, depending on the material's crystal structure and processing history. Number 6 is discoloration. Graphitization can cause discoloration or darkening of the material, especially in the presence of other phases or defects. Number 7 is delamination. In composite materials, graphitization can lead to delamination or debonding between graphite layers, which can weaken the material's mechanical properties. Number 8 is microcracking. Graphitization can cause microcracking or the formation of small cracks within graphite layers or between different phases, which can further compromise the material's mechanical properties. These are some common characteristics of the appearance or morphology of graphitization damage. The specific features and severity of graphitization can depend on various factors, including the material's composition, thermal exposure, and processing history. Prevention or mitigation. Based on API 571, prevention or mitigation of graphitization is recommended by using chromium-containing low-alloy steels can help prevent graphitization during long-term operation above 800 degrees Fahrenheit 427 degrees Celsius. Graphitization is a process where the carbon in steel or cast iron reacts with oxygen to form graphite, leading to a loss of mechanical properties and potential failure. The prevention and mitigation of graphitization damage involves several strategies. Number 1 is material selection. Using high-strength, low-carbon steel or other materials that are more resistant to graphitization can help prevent the issue altogether. Number 2 is heat treatment. Heat treating certain steels can help reduce the likelihood of graphitization by removing excess carbon from the material or altering its microstructure. Number 3 is surface coatings. Applying protective coatings can prevent the formation of graphite by creating a barrier between the material and the environment. Number 4 is moisture control. Reducing or controlling moisture in the environment can slow down the graphitization process. Number 5 is cleaning and maintenance. Regular cleaning and maintenance can remove contaminants that may accelerate graphitization. Number 6 is inspection and monitoring. Regular inspections can help identify graphitization before it becomes a critical issue, allowing for prompt action to be taken. Number 7 is repair or replacement. In cases where graphitization is severe, repair or replacement of affected components may be necessary. Number 8 is implementing safety precautions. Following safety guidelines and protocols can help prevent accidents and failures caused by graphitization. Inspection and monitoring. Inspection and monitoring methods used to detect graphitization damage in materials, particularly in the context of nuclear reactor components and other high-temperature applications, include several techniques. Number 1 is visual inspection. Basic visual examination can sometimes reveal signs of graphitization, such as surface cracking or changes in surface texture. Number 2 is ultrasonic testing or UT. This non-destructive testing method uses high-frequency sound waves to detect changes in material properties, including the presence of voids, cracks, or changes in microstructure due to graphitization. Number 3 is eddy current testing. This is another non-destructive method that can detect changes in electrical conductivity, which can be associated with graphitization. Number 4 is X-ray diffraction or XRD. This technique can be used to analyze the crystallographic structure of materials, allowing for the identification of phases and any changes due to graphitization. Number 5 is microscopy. Scanning electron microscopy, SEM, or transmission electron microscopy, TEM, can provide detailed images of the microstructure, allowing for the identification of graphitic structures and the extent of damage. Number 6 is thermal analysis. Techniques like differential scanning calorimetry, DSC, can assess changes in thermal properties associated with graphitization. Number 7 is mechanical testing. Evaluating the mechanical properties of the material, such as hardness or tensile strength, can indicate the effects of graphitization, as these properties can change significantly due to microstructural alterations. Number 8 is magnetic testing. Changes in magnetic properties can also be indicative of graphitization, particularly in ferromagnetic materials. For safety and accuracy, a combination of these methods may be used to establish the extent of graphitization damage in materials effectively. Thank you.